And we're live, and welcome to another Practicalli Clojure with me, John Stevenson. Thank you very much for joining me. Today I'm using the OBS software, so hopefully it'll be a smoother video transitioning between webcam and the desktop. And yeah, if you have any feedback on the video, please let me know. So this week we're going to cover some more 4Clojure exercises. So we're going to start with 4Clojure 39 and hopefully get to 4Clojure number 40 as well. And these both cover the subject of sequences. So we'll talk about sequences a little bit in Clojure and what they mean as well. Okay, let's get going then. So if we switch over, oh, there's me. So when I'm doing things in Spacemacs now, you should be able to see the keys I'm pressing in the top right hand corner. So I'm pressing the up and down arrows as well, so it'll give you some idea about what I'm doing in the editor if you're using that. Again, I'm using Spacemacs because it's the best editor for me. There are other editors out there for Clojure as well. You don't have to use Emacs. Okay, let's get going. So let's have a look at the 4Clojure challenge. Oops, that's not the right one. There we go. Let's go to number 39. I haven't really found a good way to navigate except for just typing in the number of those. So 39. What it's asking is to write a function which takes two sequences and returns the first item from each and then the second item from each, and so on and so on. So we're doing 1 and A and combining them, and we get 1A, and then so on and so on and so on. And so we're getting the same arguments. It's fairly straightforward in terms of defining a function, and so we just really have to focus on how to actually combine them. And we've got a special restriction here called interleave, so we can't use the interleave function. And pretty sure that's going to make it, if we could, that would just be the answer, just putting interleave in there. So let's switch back to our source code. I did make that a little bit bigger. Let's make that a little bit bigger. There we go. Cool. Oops. Oh, if I do that, yes. There we go. So here are all our tests that we've got. And so let's deconstruct the problem a little bit. So we go and write a function. It's going to take two arguments, and those arguments are going to be sequences. Then we need to kind of somehow iterate over the sequences in parallel, and then take an item from each, an element from each sequence, and combine them, and then keep on going until there's no more sequences. Yeah, so this is interesting, and there is an interesting one in the if we look at the second test, actually see what it's doing is actually failing at the if there's nothing in one of the sequences. If one of the sequences ends, then we end as well, because there's 5 and 6 in here, but there's no 5 and 6 in the answer. And the same thing with here. There's 1, 2, 3, 4 in here, but there's only 5. So when you do the first pair, so it's not padding for the longest one. It's just for the longest sequence. It's just matching up pairs for the shortest sequence. So that's interesting. And we can't use interleave because that would just work. So let's see how we can actually tackle this. So let's have a look at what a sequence is itself, because it is talking about sequences. And so, to put simply, it's just a sequence of elements. It's just and elements can be any kind of things in that are legal in Clojure. Excuse me. So elements can be anything that is legal in Clojure. That can be obviously numbers, whether it be integer or decimal numbers, ratios. It can be characters and strings. It can be symbols that point to functions or point to data. And it can also be function calls as well, because function calls, when they're evaluated, they are just return a piece of data. So a simple element would be 1, 2, 3, 4, and they're usually represented as a list. So in Clojure, they would be they'd be put in as a list 1, 2, 3, 4, 5. So that would be our linked our list, our sequence representation. And if we just want to treat it as a sequence, we do need to remember to either wrap it with the quotes function. Oops, I didn't want to do that. Or more commonly, to just use the little quotes symbol, which is just the single quote there. So that just means that we won't treat the first element as a function call as we do normally. That's the default position. We will just treat this all as data. And so this is pretty efficient. It's a pretty simple way to represent a sequence of data, because when we want to navigate this data structure, we will just go to the first element, and then the first element points to the next one, and next one, and next one, next one, and so on and so on. So it's very easy to add. It's very easy to work with the list. You can just basically start at the beginning and just work through it until the end. And so this is why it's like this linked list is used for all the function definitions and basically most of the code. And then if you need some optimizations, if you need an index, then you can use vector. If you need an associative array, then you can use a map, which associates a key value pair together. But you can also treat lists, you can also treat vectors as a sequence as well. You don't have to use it as an indexed array. And you can use these common sequence functions on there, so first, rest, conj, cons, and so on. Conj is an interesting one because it will it will work slightly differently depending on whether you give it a list or a vector. So if you're conjing onto a list, it'll join it onto the start because that's the most efficient thing to do for a list. If you have to add numbers, say if you've got numbers 1 to 10,000, if you wanted to add 10,001 to it, you'd have to traverse through all of the 10,000 numbers first and then add it to the end. So when you're adding things to a list, by default they'll be added to the start of the list. So if I was going to add another number in here, 6, then that will be added to the head of the list, the start of the list, and it would point to the next value, which is 1. So that's the most efficient way to add things to a list. Whereas a vector has there's an index in here, so there's like this idea of an index. Let me press 1, 2. So the index starts at 0. So we'd have 0, 1, and 2. So the R1 is at index 0, R2 is at index 1, R3 is at index 2. So there's that extra index on top of the vector, which allows us to go and add things at the end there. So we can access a vector using its index and do random access in a fairly efficient time. And so for this case, for the 4Clojure one, it doesn't actually matter if we use vectors or lists at the end. This is something that confused me initially when I was first learning Clojure, because it's when you're comparing a list and a vector, it's actually just comparing the values inside those collections. It doesn't really care about whether it's a list or a vector. You can just treat them both as sequences and compare the elements to see if they're the same. If the values inside each of them are the same, then they're equal. Let's see, right. So that gives us a little bit of insight into sequences. There's a lot more information about sequences you can go and read. There's a whole section on sequences on the Clojure. Where is it? Oh, yeah, there we go. Oops, I was just looking for the link there. Yeah, so if you go to Clojure, clojure.org sequences, it'll go into a lot more detail. And sequences can be lazy as well, so you can actually use them lazily. So if you've got a massive sequence, if you've got a massive amount of data, you don't have to load it in all at once. You can just work with the information that you need from the sequence. You don't have to pass it all. An example of that would be if we did range by itself, it would just generate an infinite number of integers, and our computer can't hold an infinite number of integers, so that's be a bit of a challenge. But if we put something around it, then we can kind of make it lazy. So if we just take 10, oops, excuse me, then it's only going to lazily evaluate range until it's got just the number of values it needs. In this case, it just needs 10 values, so it'll generate it from 0 to 9. Let's see if the REPL is working. Oops, is my REPL working today? Am I connected? Oh, I'm not connected, so I forgot to start that. There we go. Let's just start the REPL. REPL. I'm still waiting for somebody to write a good song lyrics for REPL to the music of Rebel. There we go, it started. Let's evaluate this. So it's comma E. There we go. So we've got a range now of 0 to 9. So instead of range generating infinity, which is tricky to deal with, it's only generating 10. So that's kind of one example of lazy, but there are many others. We'll cover that in another session, I think. So let's get on to solving the challenge. So we could use interleave. Well, this is how interleave is working. We can see how it's giving us the right results, but unfortunately we can't use it for this challenge. So we could use loop recur. I didn't do one for this time now, but yeah, we can do pretty much anything with loop recur, but it's going to be a lot of work, or at least a lot of code. And if we're iterating, then we usually look to functions like map and reduce and apply. Those are the kind of the very common functions for iterating through a collection. And I know map will allow us to iterate through two or more collections, two or more sequences at the same time. So like if, for example, we've got map, we've got a vector 1, 2, 3, and 4, 5, oops, not 45, 4, 5, 6, and I'm going to put an extra number in here just to show for details. So we want to map, but we want to map a function over there. So we need to think of a function to do that. We can just use something simple like plus for now. And so map is going to add the first value in this first sequence to the first value in that sequence, and then give us the results and go all the way through until it gets to the end. And we can see what happens with the extra 7 on here as well. So you see it's taking the first 3 values because that's what there is in the collection there and adding them together. And it's dropping the 7 because there's nothing matching in the first collection there. So it kind of does a bit of what we want. And we might just be able to write a function there, and yeah, we could implement our interleave like that and hopefully get the right results. So here we've got an example. Here I've just written a very specific inline function. So I'm just calling function, so it's going to be called straight away. It's going to take 2 arguments, which are the 2 sequences, and in this case all I'm just doing is just returning a vector collection that just has those 2 elements inside it. So this is probably the simplest kind of thing I think of, and it's and then this is going to take 2 arguments. So this is the 2 arguments that go to the function is going to be mapped over, and as you can see, we're kind of getting the right answer. So if we go to the where's the interleave one? Can we see them both at once? So we want 1A to B 3C, and so we've got 1A to B 3C. So we've got the right values combined, although we can see that it's not the right structure. So this wouldn't quite pass our tests because it's not returning. It's returning a nested structure rather than a single collection or a single sequence. So I'd need to get rid of the values in these vectors. So actually creating a vector in there isn't particularly helping us. It's giving us the right answer but not giving us the right result. I can't not use. I need to use something in here because I can't return these 2 values without being in some kind of vector, because it would only return the second one. I think it would just return the last thing that we evaluated, which in this case would be the second value. So we'd actually miss off a whole bunch of values in there, I think. Let me just see. Yeah, so we just get ABC. So it's completely ignoring sequence 1 because that's the first thing in there, and sequence 2 is the last thing in the list. So that's the last thing that gets evaluated. So that doesn't help us. So we could use we could take the results here and do something with them to make that a nicer, well, to make that the right structure that we want. And there are a few things in here. So there's conj and conj we could use, but there's with these 2 functions you need a mixture of a collection and a value. So you're adding a value to a collection, you're not adding 2 collections together. Into, we could use reduce conj in there again. That might not be the right answer. It might work. But there's also concat, and so this is a concatenation of elements in the supplied collections. So that seems to be more promising. And so I just looked these up in Clojure docs. Although I think I know most of these by now. They just pop into my head. And so we've got concat, and it's taking, if we give it the 3 different collections, then it'll just create 1. So that seems to work okay. However, we've kind of made the mistake here accidentally on purpose to show that if we just concat, because we're actually giving it a different structure, we're actually giving it something else. Let's show you what we're actually giving it. So we're actually giving it this structure. So this is just a single list. So we can't concat the list with something else because we haven't given it anything else. There's nothing after this list here. So we would need to actually iterate through this list to be able to concat each of those collections together. So that's not good. So I think, oh yes. Did that work? It might have worked, yeah, because I did the I didn't think this worked, but then I realized I'd missed off the little quote in here, so it's very easy to do when you're dealing with lists. This is why I usually deal with vectors and maps. It's a lot easier. It's a lot less likely you'll miss off that. I'm going to delete that, I think. Yeah, there we go. So we've got map concat. So we do that, we're still not getting the right results. So it's not map that we want, but it's actually reduce. So, which actually makes sense because we've got multiple elements in here. We've got 3 elements in our list, and we want to reduce them down to a single collection, a single sequence in this case. So when we reduce with concat, then we're actually getting the right answer in the right structure. And we could also use apply as well. I'm not going to go to the differences right now. I've done that in other videos, but essentially in this case they work exactly the same. And then there's so we can create this reduce around it, so we can take the results of the mapping of this function over our 2 different collections, and then we can take the results of that and we can reduce by concatenating over those results from the map expression, and we get the right result. So that works. That gives us an answer. But there's quite a few things in here. So we've got reduce, we've got concat, we've got map, and that seems quite a lot for a fairly simple problem. If we're just doing interleave, perhaps there's something else we can do. So what I did was actually go on to the internet and just did a Google 4Clojure map, and that takes me to the Clojure docs website. And so this is really useful because it tells you what the doc string of the function is, and then you can see some examples as well. But it also, right down the bottom, let's do that, it's quicker. Ooh, there's quite a lot in there. It gives you the see also section. So there's a whole bunch of extra functions that are related to map as well. So things like map v, which is the same as map but just returns a vector. So if you don't want to return a sequence, you can return a vector instead. And then we've got map indexed, which is really cool. So it will basically map based on the index of the items rather than the values. And juxta is quite a cool one as well. I think we've used that. I'm not sure if I've used it yet, but we'll use that in some of the 4Clojure examples. But then I came across MapCat, which returns the result of applying concatenate. So we want to apply concatenate that to the result of mapping a function to collections. That sounds pretty much ideal for what we want. And then there's lots of examples here. So MapCat reverse is going over our collections here and bringing back a single collection, a single list. So that looks very promising. Let's go on back to the code and see what's going on. So let's try MapCat, and so yeah, so we MapCat our function over here over our two values, and we get the right results. That's pretty good. Yeah, so I'm quite happy. We get a fairly decent golf score from that. But can we define it any further? Let's have a look. Well, yeah, so we're kind of just doing something very simple. We're just returning the two values in a vector. So it's cool. Yeah, I mean, we could use a short form of the function definition in here, but is there a function that just does this for us rather than having to write our own function? If there's a function in Clojure core that does this already, then that's preferable than to writing our own function. So here we've got vector 1 and 2. So if we just use vec and vector, they will create vectors for us. So what's the best one to use? So if we do vector of 1 and 2, that's just going to give us a vector. So that's kind of the same. So we could use vector instead of our function, because we're going to give it two arguments from the map, and it will process them together and put them into a vector, and then if we're using MapCut, it's going to concatenate them together. And what happens in what happens with a vector there? So if we give it two collections, it's going to make a collection out of those. So it's not quite well, but we're actually not doing that. We're actually giving it we're mapping that, so we're actually giving it the individual values because we're using map with the. If we use map with a vector, then that would work. And so if we so if we use if we take that's not what we want, is it? No. Where's our values? Our initial values. So we want 1, 2, 3. G. Oh. So if we MapCat a vector over that, over the values, then it's giving us the right result. So therefore we can go back to our 4Clojure and we can just say, well, okay, we're going to give it MapCat vector instead of the blank that's there. So let's go back to the 4Clojure page. And where are we? Oops. No, oh, we lost it now. Oh, there it is. Yeah, so we just want to put in, so rather than putting our map function in there, we can put our MapCat vector in there, and oh, I already have done. Yeah. And let's just run that just to show it's actually working and test it's working for all the results. We only really tested it for the first one. Usually that's fine, but in this case it might have tripped up on the fact that these have a different number of elements in each one. But because map takes care of that for us, so the map function and MapCat function actually will terminate if at the end of the shortest sequence or collection that you give it. So that we don't have to worry about that extra bit of code for us, which is something else we would have needed to include in the loop recur. But yeah, luckily all our tests have passed, so the same code works for all of them, so that's great. We can go ahead and have a look at the solutions as well. So that's our solution. It's pretty good. Somebody's done they've written a recursive function here, and so this is just a slightly higher level up from a loop recur. So the set conditions, so we don't loop through, we don't recur through, we don't iterate through this like forever. We've got a condition that will break us out of the recursive function. And so it's testing to see if either of the collections are empty, so that's quite nice. If it's not, then it's going to run concat and map first. Okay, So it's basically adding the two values up together, and then and then it's calling itself. So it's going to go around with the rest of the collection. So it's going to get the first two elements from the collection, and then it's going to call itself, and it's going to map. Okay, right. So it's mapping first. So it's getting the first, because this is going to all be a list of vectors. It's going to get the element from there and going to concatenate them all together once it's generated. So this will kind of go through round and round this circle of this else condition until we get to the empty, until one of the sequences is empty, and then it'll all kind of evaluate out into the result. So that's not too bad. So that's our example of a loop recur, really, and there's another one there as well. So you can see there's an awful lot of code there for just what we've done comparing to our own answer. This is up more low level, and this is very powerful. We can do whatever we want in here. We can change and add any kind of conditions in here we wanted to. But if there's existing functions in Clojure core, then that just makes it easier and simpler and easier to read, because these are kind of standard pieces of functionality that the Clojure developers will learn. I don't think there'll be anything else that's there. Oh, MapCat list. I think they have only put that on there just because list is got fewer characters in than the word vector. So this will have a slightly lower golf score just by a couple of points. But but essentially the same, because list is when we're comparing things, we're comparing them as sequences. So when we compare list and vector together, then they're just going to be equal. Anything else is doing anything interesting? No. MapCat list, MapCat vector. Oh, that's a bit. What if? Oh, okay. So these are functions that's calling a function. Yes, or returning a function. No, it's calling. What? It's a function within a function. This one's a bit crazy. Okay, I think this one is a little bit overthought, which is very easy to do, especially when you're first starting. It's very easy just to kind of learn a few tools and learn a few functions and just apply them. We never really used flatten. We could use flatten. It's a bit of a blunt tool. It will just discriminately flatten anything, but it's usually considered a bit of a code smell if you're using flatten, because you're not really flattening in any particular way. You just basically just remove all of the nested structures and just return the values. In this case, it would be fine, but in production, then often that's kind of like a bit too much of a blunt tool to use. And that's it so far, I think. Yes, okay. I don't think there's anything else to mention here. Yeah, that's it. Cool. Okay. Any questions? I don't see any questions on this. Let's just check to see if that's all working. It seems to be working okay. Yep. Okay, let's go to the next one. So next one is number 40. Let's just change the number here to 40. There we go. And we're working with another sequence. And so it says it's easy. I mean, it's not easy until you're familiar with sequences, but it's not massively challenging. It's very similar to what we did in the last one, I think. So we're writing a function which separates the items of the sequence by an arbitrary value. So basically, we're injecting or interposing a value in between the values of a collection or of a sequence. So here we've got 1, 2, and 3. We're going to return 0, 2, and 3 with 1, 0, 2, 0, 3. But we're not putting anything at the end, so we're not just going to kind of loop through and add a 0. We have to be a bit more clever than that. We have to know that when we've got to the end, and to not put the value after the last character. So we can't just put something that after each element, we have to put something specifically in between there as well. Although we could put one after the element and then just drop the last, but that feels like cheating. And as you can probably guess, Interpose would just do this for us, but it's a chance to go and have a look at Interpose as well. Okay, let's switch back to the code. And save that. So these are on the internet. I've pushed them up to my repository. I'll show you that at the end. Let's see if we do Alt, open a file, and we want to do number 40. There we go, interpose a sequence. There we go. So we've got our tests here. Is anything? I don't think there's anything particularly different, but they're all taking a value and a collection. This one's got a value and a collection. This one's quite nice because normally if we do things with a string, we usually have to use the Clojure.string libraries because they're more specifically working with a string. So when you run functions of a string, if they're just some of the generic functions in Clojure core, then rather than getting a string back, you would get a sequence of characters. And that's what a string actually is. So if we, for example, if we did the classic one says reverse a string. Let's see. So this is just the Clojure core reverse, and you can see it's returns the string in reverse, but there, instead of being a string, it's individual characters. And so to get the actual right result, then we'd have to do something like apply the string function to that. And then when we evaluate this now, it should give us a string. There we go. So we've got a string there. Normally you would use the Clojure.string, and then there's a reverse. There is a reverse. There we go. So there's a reverse function specifically for strings. If you do J now. So we don't need to do the apply for that because the Clojure string takes care of it for us. But in our if all of these were strings, then we could maybe use a specific Clojure string function. But because it's a mixture of numbers and strings, then luckily the test will fix the characters for us, so we could just use normal Clojure core functions in here. You don't have to worry about so looking for a string and then putting a condition that if it's a string, then we have to kind of convert it from a sequence of characters to a string again. So that's taken care of it for us, which is nice. So what do we need to do? We need to write a function that takes two arguments, value and a collection. So we've just kind of done something similar before that in the last one. And we need to work, irrespective of what types of values there are. So again, the string is taken care of by the apply string on the results, and the function should place a value between the elements. Yeah. So we should put the value in there as well. Okay, that's all. But we can't use interpose. Interpose would just work. So these are all true just by if we use the interpose, but we're not allowed to use that. We could go and look at the source code if we wanted to. I did do a loop recur from here. You can see we've got quite a bit of code in here. So we've taking in a value and the collection as a function, and we're going to set the current collection to the initial value of the collection, and we've created this new collection local name, which we're going to have as an empty vector to start with, and then if the count of the current collection is less than 1, then oh sorry, greater than 1. So if there's basically more than one element in the collection, we're going to basically recur around it, and we're going to pass back the rest of the collection. So this is our iterative part here. So we're actually reducing the number by 1 of the contents of the collection. So this rest collection will go and get mapped over to current collection, and then we'll do then we'll conjoin the new collection, which is initially empty, with the first value of the current collection, and then the value. So that will take the, in this case, it would take the 0, it would take the 1 as the first value from the current collection, and then the 1, and conjoin them, and then pass that back as the new collection here, and just go round and round. Did I? Oh, that says nearly right. What actually does it do? Oh, so it's nearly right, except what I did was if the count is greater than. What did I get wrong? Oh, that's interesting. Maybe I got the @ sign wrong. It's something I always get a little bit confused about, is which way that goes. I think yes, greater than 1. Yeah, that's right, isn't it? That one. Oops. Wrong button. Oh yeah, I didn't press shift. There we go. Does that fix it? Oh, okay. Oh yeah, no, that is right then. Okay. So it was right before that one, yes. Oh yeah, there we go. So it's mostly doing it right, but it's terminating before, because we're passing the new collection back if the count is basically 1 or less. It's not going to get more than it's not going to get less than 1. So we're missing off the last value from the collection. So what we can do is just conj that the first value of the collection, the current collection, which at this point when it's 1, when the count of the current collection is 1, then there's only going to be 1 value in that current collection, and so we'll just grab that, and I suppose we could use last as well to make it more meaningful as what we're doing, but essentially this gives us the right answer here. But that's quite a lot of code to do it, but it gives, we can do whatever we want in there if we wanted to. We can write a recursive function. Oops, my first go didn't quite work, but yeah, so instead of interpose, I've written a function called impose, so we're imposing a value in between the collections. And so yeah, we've got a condition here, so greater than equal than 1, then we're going to just return the collection, else we're going to concatenate like the first value of the connection and then just interpose all the rest. So we'll like iterate through everything, and it will give us all the right answer at the end. Boom, there we go. So that streamlines it a little bit, but it's still quite a lot of code compared to just being able to do interpose. And we could use interleave now that we've learned interleave. So we can kind of interleave, but we want everything, but if we interleave something, it would put the 0 at the end. So in this one, where we're taking in, we're going to interleave the collection, and we're going to repeat the value. So it's just interleaving the collection with the values. So it's just going to repeat the value over and over again until the end of the collection is reached. So here, if we're passing in 1, 2, 3, then this repeat is going to we're going to repeat the value of 0 3 times. So it would give us 1, 1, 0, 2, 0, 3, 0, and then we're wrapping that in the but last, which is an amusingly named function, but it's giving you everything but the last value. So if we have if we do but last on here, then we've got 1, 0, 2, 0, 3, 0. Oops, not 30, 3, 0. There we are. Then it's going to give us everything but the last number. There we go. So and that gives us the answer. So it's a kind of a sneaky-ish way of doing it, I think, but it's okay. And then there's this. This is the same, basically just with a different value here. So here we just interleave with the repeat value of the collection, and we're just wrapping it in next. And then there's another, we can use MapCut as well. So we're basically putting the list around the value and an element of each element of the collection. So we're basically building up a list of lists, and then we concatenate them together, and we just drop the first one. So we've got the end result there. I quite like the kind of next interleave. I think this is quite nice, and the but last I think is quite an okay solution here. I don't think there's a perfect solution, but I think these two are the ones I enjoyed the most, I think, or the ones I'm happiest with. Any questions? No questions. It's so let's go back to here. Which one did I use? Did I put one in here? I put that one in there. Yep. So let's just run that just to make sure it works. There's no smoke and mirrors here. Yeah, it's all working. So look at the solutions. Yep. So this is writing a function, a recursive function, and there's but last rest. Ooh, what was that one? Oh yeah, that's just the syntactic sugar around declaring an inline function. Anything else but last? MapCat. Interesting, yeah. So there's like a few variations, but there's no one kind of like obvious absolute answer. This is software, so that's not unusual, but there's a few different ways to do it with very similar kind of functions. Yeah, okie dokie. Alright, no questions on that one, so let's see. Do we have time for another one? Oh, we've got 10 minutes. Let's have a quick look, see what the next one is, see if we can squeeze another one in. What is this one about? Drop every nth item. It says it's easy. So write a function which drops every nth item from the sequence. Oh, so this is dealing with sequences as well, so let's do this one again as well. I think I've set this up. I think I've actually done this one already. Let's go back here and let's open number 41. 41. Oh, there we go. There it is. And so it's writing a function. So we've got our collection. So we write a function that takes 2 arguments. The first argument is going to be the collection, and then how many nth item of the sequence we want to drop. So we're dropping every third item. So here 1, 2, 3 is gone, 4, 5, and 6 is gone. So it's the third value. It's not the index. It's actually the element in the collection that we're dropping. So we're not using the index. There's a difference between index because indexes are all 0. Okay, so we could use filter. Oh, oh yeah. So filter is. Oh yeah. So if it's okay. So we're dividing by 3. So we're going to divide each of the values by 3, and if the remainder to get the remainder, and if it's not 0, then we're going to keep that value. So basically, we're going to divide each of these values by 3. When the result is 0, then we know that that's going to match the test. So this is quite a explicit kind of test. It's not doing positional; it's doing numerics, which is okay for the first test, but it's not going to work for the second test because they're not numbers, they're keywords. But if they were all numbers, if we're just dealing with numbers, then that kind of works, I think. I think that gives us a result. So we can either filter, like do a negative filter in here, because it's going to return only things that match. So if we return things that only matched the remainder by 3 is 0, then it would give us the inverse of this. It would give us 3, 6. So we put in a not equals in front of that, so that if it's not equal to 0, the remainder of dividing by 3, then we're going to keep that and return the results as we have done here. And so there's an opposite of filter, which is remove, which is just remove everything from the collection that matches the condition that we're doing here as well. So this is just the inline function we're calling. So we're just giving a function to remove that just basically tests to see whether we're dividing by 3, and if it's equal to 0, then that's the value we want to remove. So that works for the first test. It would probably work for the third test as well, but not for the second one. So the second one, so we could use partition. I do like partition. It's quite nice. I think it's a very interesting function because you're doing a lot of transformation of data. So you're transmogrifying data from one structure to another, just like you're transforming a caterpillar into a butterfly. They're both the same kind of creature, but you transfer it into a different shape, a different form, and you can then write algorithms that are much more simpler because you've transformed the data structure into something that is easier to work with, is more relevant to what you're trying to achieve. So here we're going to partition things up by 2, which does mean that we'll is that true? Oh, okay. Oh yeah, so if we partition it by 2, we could kind of drop the first one there, but then it's the last one there, so it doesn't quite work. So but we can partition, so basically grouping the first 2 values, and then the second 2 values, and the third 2 values, and the fourth 2 values, and so on. But we can also introduce a step into that as well. So the first the first argument to partition is the grouping size. But then the next one is you can do the step you're doing as well. So here we're actually stepping over the third value, so we're not actually including it. And then, I have used the naughty flatten one as well, which in this case is okay because we're not doing anything particularly interesting, but there might be a better way to do it than not use flatten. Yeah, so we're essentially taking the results of these groupings and just flattening them together, so we get the right answer there. So that's one way to do it, purely based on position. And this is just the short form of this flatten in a. So yeah, we'll just put it into a function here. Lickety. Oh, my cat's come to join me. Hello, Puss. You come to do some coding. Wow. Yes, Johnny. I like coding. Hello. So we did a function. Oops. Come here. Which takes the collection and the step. Hello, yes, I'm trying to type. And there we go. Yes, somebody wants attention this morning. There we go. Just for a change. Right, what was I doing? Sorry. So I'm doing flatten. Flatten on the partition, and we're going to decrement. Oh, okay, right, yeah. So we want to get the grouping size. So we want to take away a value of 1 from the step, the value that we're passing in. So we passed in 3, but so we want a grouping of 2. So we use dec, that will convert 3 into 2 for us. So that's a step. So that'll give us our partition size, and then we want the step size, which is just step. And coding with cats is fun. And then the collection itself, which is, you know, you're on YouTube, don't you? There we go. You smell of garden. So that's what we're doing here. So that basically just puts it into a function, so we can include it into 4Clojure. Okay. So if we put this in, we can see that it's not quite passing up all the tests. There we go. Do you want to do some coding with me? Yes, yes, please. Yes, please. Boom. Somebody's been cutting their grass. There we go. So let's run that, and it's passing the first 2, but it's failing the 4th one. So the 3rd one, and oh yes, because let's have a look, see what that's doing. Tab. Oh yeah, so it's because when we partition something, yeah. So let's just show you what we're getting. So if we partition a collection, so we're going to partition by 2, but we've got an odd number of excuse me. If we've got an odd number of values in our collection, so 1, 2, 3. Oh, there we go, cat free. And we evaluate this. You can see it's actually only returning the values that are in the groupings that it's created. It's missing off the 3rd value. But if we so we could pad. I think my first idea was to pad something, but then what to pad it with? We could, and we can't pad it with just zeros because flatten wouldn't work then. So it's kind of showing the. So I tried a few different things about how to flatten something. And oh yes, so I decided to pad it with nil. Because nil, when you flatten it, it just returns the empty set. So that would actually just keep on flattening nil to make it disappear. So that actually does give us the right results in this one. But it just seems to be doesn't feel quite right, and it kind of does show you the kind of the way that kind of flatten is kind of changing the direction you're going into the solution, which is making it a little bit more complex because you're trying to impose things in here. And we've only really looked at partition, and there's some other aspects to partition we can use. So that one it does work when you're putting in nil, but it just feels like we're forcing this this padding into the situation. But if we do something like if we do partition all, so this returns it returns the partitions, the groupings as before, but it's also going to include the partitions with fewer than the grouping number, so fewer than n numbers. So if we do partition all, we have a grouping of 2, but then we give it an odd number of values, it's going to return all of those to us as well. So we get the 3 involved there as well. So if we update our, our answer to be partition all, then that's working. So we can kind of, let's do the full version of that as well. So take that one. And so that must be partition all. There it is. There it is. So it's the same as before. Still using flatten, which is okay for now. I'm sure there's a better way to do this than that, but let's have a look. And yeah, we could do the loop or even recursive function, but I think this one's the more sensible one. So let's just do that. Let's go put it back into our tests in here. So partition all. So is that going to pass the last one? Run. There we go. So yeah, when we're partitioning it by 4, we get the first 3 in there, but then there isn't a second 3, so it wouldn't return the 4 and 6 without partition all. But because we're using partition all now, it's going to return the 5 and 6 as well, and then flatten them all together. Let's see if there are any solutions without flatten. So that's written oh, this is interesting. So they've got a multi-arity function here. So there's a function that if you call it with 2 arguments, it's going to just run this body of the code. And if you call it with 3 arguments, if you call drop n with 3 arguments, then it's going to it's going to run this piece of code instead. So, and this is quite useful, it's quite interesting because if you call it with 2 arguments, it's actually going to call itself and give a default 3rd argument here. Interesting. But essentially it's doing the check. It's using mod instead of rem to see, and then pretty much working the same as before in the recursive function that we did. A keep index. Oh, that might be quite nice. Yeah. Let's have a look. So yeah, so it's got the test again when the mod is greater than 3. So it's not using partition, but it is keeping the index. Let's have a look at that one. That might be a useful one to explore. Let's have a look. Oops. Why is my... That's not, oh, I don't have my snippets in here. Oops, that's why. There we go. There we go. So this is a keep. And so if we look at the docs for this, it's going to return laser sequence of non-nil results applying the function to the index of the item. So it's using the index of the things it's returned. So it's going to keep the index. So let's see if that's. So we can see how that's working with some debugging. And we need some. Let's take the tests here. Take the test value, come back down, and we're just going to call this function. So I'm just going to wrap this function. So space KW for wrapping it. So I've turned this from a function definition to a function call, and then just toggle over to the other end of the thing there and just put in our values we want to call this function with. So this is just a function definition that's now in a list. So this function definition will now be evaluated and called as a function, and with these arguments. And does it work? Let's see if it works. It does work. Let's see if we can see how it works. So let's put the debugging and the B. So I'm going to set a debugger on there. So I think it's S for sequence. So the sequence that we've passed in is a vector. I'm just going to use N to step through these. And so incrementing I. So we've got a function I. Where does that come from? Ooh, interesting. So we've got, oh, is it from the 0? Okay, there we go. So X is 3 from the step that we've done. We're seeing whether we've got the mod of 1, and 3 is 1. So that's true. Oh, so is there a remainder kind of thing? And then we've got so A is 1. I'm not sure I followed this one. I might need to go and have a look at this in a bit more detail. Let's see next. Oops. And that's 2. So we're just incrementing the numbers, dividing it by 3. Is that right? Okay, so it's gone through the collection. It's created 1, 2, 4, 3. So it's got rid of basically everything you can divide by 3 with 0 remainder, and then it's just returned that. So I'm not quite sure what the keep index is doing here. I'll have to go and have a look at that one in a bit more detail. What else is there? Interesting. Is that more complex than ours? I do like ours because it's very kind of generic in terms of what it's doing. It's not testing. Oh, okay, right. So this is right. So the index. So it's testing on the index rather than the. Oh yeah, of course, yeah. Because our we can't divide things by. We can't divide these values by, in this case, 2. But we can see if the index, which the index will be 3 in this case. We want to if we want to get rid of oh no, yeah, so if we want to get rid of these ones, if we want to get rid of B, then that index is going to be 1, and so we can use the index value of the elements to actually see whether we're supposed to remove it or not. So that way it doesn't matter if these are values or if these are numbers or any other values. It's purely doing the positional thing of seeing, well, okay, that's in position 0, that's in position 1, and that's in position 2. So we have to decrement that value a little bit, and then we can remove them based on the index of this vector. Obviously, that's not going to work if you're passing in a linked list, because it doesn't have a index. There we go. Oops. I have to run it again to look at the solutions. Let's just see if there's any more interesting solutions there. That's also using keep index. So partition all. Apply Concat. Yeah, that's probably nicer actually than doing filter. MapCat identity. That's another thing. I quite like this. Apply Concat to that. Does that mean you can do MapCat? Maybe it means MapCat. You can do that. That seems to be interesting. Oh yeah, that's using MapCat. I'll keep indexed. That seems to be the common ones it's using. Loop recur. Oh yeah. I mean, just looking at that, it does require you to just sit down for 5 minutes to actually read it, or just bring out the debugger and walk a step through it. But yeah, I think this one is probably my kind of favourite of these. That's quite nice. Yep, everything else. MapCat but last, interesting. Okay, there we go. And Mike Fikes of yep, okay. So I'm going to put this one into here as a nice answer, and I'm going to do the I'll do the normal function version of that as well, and that's it. Oh, that's amazing! Thank you. Yeah, so that's it. I'm going to leave it there. I'm going to push these up to the repository, which is on GitHub, and I'll put the link in the show notes. So it's me, and then 4Clojure, F-O-U-R, Clojure, if I spell that right. Oh, did I not spell that right? Oh, that's not gists. I keep doing that. Just the normal GitHub, please. So there's a whole bunch. If you go into source, or just clone this, and there's a few more if you want to go ahead. There's a few other ones I've done there. So I'll be doing, I guess I'll be doing the 42 onwards, which I haven't actually done yet. So I'll do that this week and push them up. We'll cover them next week, unless we get any ideas about other things you'd like to cover. So if you do have any other ideas about what you'd like to do, please let me know. And you can reach out to me on Practicalli via Twitter, also the Clojurian Slack channel as well. So if you just go to my web page, there's a whole bunch of ways you can reach out to me as well. So you can reach out to me via Slack, via GitHub and do some issues if you find any issues with any of the 4Clojure ones, or you've got any other ideas or solutions you'd like to share. And then also by Practicalli _li as well. Okay, thank you very much for joining, and I'll see you next time. Thank you. Bye bye.